Hello, we're just going to look at lessons 22 and 21 very briefly. They're strongly related. We're talking about gravitation, gravitational field strength, and this principle that any mass exerts some kind of strength or some kind of field around it that draws other objects to it. This principle was contemplated by Sir Isaac Newton, a British mathematician and physicist that I'm sure you've heard of. He's the guy behind Newton's 3 laws of motion. In 1665, when he was a young student in London, he escaped the Great Plague of London and went to his family's farm in Woolsthorpe. And for 1 year, or around a year, which he calls the Year of Wonder, he developed calculus and advanced studies in optics, lenses, and the nature of light, which you'll study next year. And also the beginnings of this idea that masses have this field, this gravitational field. And so this is where it comes from. He later developed it a little bit further. And then it's Henry Cavendish, another British mathematician or physicist, this interesting fellow. I have a link to a video about Henry Cavendish and how he developed the constant G. And I would really like you to watch that. Understanding that experiment is quite vital, and we're going to see experiments like that again in Physics 30. So the idea is that any object, so here's a mass, has around it a field strength that exerts on everything else around it. So I can have a mass over here and another mass over here, and these masses will also exert field strengths around it as well. So we have this interaction. Now, we don't experience that around us. So if I'm standing next to a desk, I'm not drawn to that desk gravitationally. The force is dependent on the mass, right? So the larger the mass, the more gravitation it's going to exert. So we experience on a daily basis Earth. Earth is a massive mass, huge mass, and it exerts its gravitation on us. You'd be surprised to know that we do sense a little bit of gravitation from the moon. In fact, the moon is what provides the gravitation for tides, and so water, which is a little bit, has that movement, is drawn to the moon, and that's why we have tides. So the mass is very important, but also distance. We are very, very far from the sun. The sun is so much larger than the Earth, so why aren't we drawn to the Earth? Why aren't we drawn to the sun? Well, it's because we're so far away. And so Newton actually promoted or understood or came to understand this idea of the inverse square law, in that the strength, or we could say the force, the gravitational force, is inversely proportional. Here's this funny symbol, inversely proportional to 1 over the distance squared that you are from that mass, or from the center of that mass. And so you can see that an apple hanging from a tree, right, is being drawn to the ground. That same force, because it's so much closer to the center of the Earth, it has a stronger force on it, or experiences more of that gravitational force than, say, the moon, which is further from the Earth. And so we're going to explore that a little bit, but it's this principle that we have this inverse square law that helps us understand. So the mass and the distance are the two parameters that affect gravity. So we have this formula, Fg is equal to G, which we'll come to in a moment, times Now remember, see I have these arrows here, and we have these double forces. One mass is pulling on the other mass. So we also have Newton's third law, that if the Earth is pulling on an apple, the apple is also exerting the same force on the Earth, which maybe is hard to understand, right? If we have the Earth, which is so big and provides this, constant of gravity, how can an apple do the same? Well, the apple is the same distance, right? We were talking about distance. And we have the same two masses at play. And so we have the two masses, mass 1 and mass 2, that are attracting one another, right? If there isn't a second mass, well, there won't be much going on as far as the forces. And then we divide by the radius, which is the distance between the centers of the two masses, okay? So the radius is the center of the distance between the centers of the two masses, and we square that value. So let's just take, for instance, this Fg. We've been playing with this for a long time. We say Fg is equal to m times g, and the mass we've been talking about is maybe a chicken that we've held up, and we time how long it takes to fall to the ground. Well, if we take that 1 kilogram chicken, right, and we say, all right, 1 kilogram, we can call that M2. So we'd say M2 equals 1 kilogram. And so we're going to leave M2 to the side here. So we're going to say Fg is equal to M2. And then we have this constant g, and I mentioned Henry Cavendish's name earlier. G is a very, very tiny number. It's calculated, and Cavendish calculated this quite remarkably. It's one of the most impressive numbers to be recognized in or developed, especially around that time. One of the most remarkable experiments. So we have this tiny number, constant g, so that's g. And then we have the mass of the Earth. Well, Earth is pretty big, it's pretty heavy. We have that on our data sheet. That is 5.98 times 10 to the 24 kilograms. And it's hard for us to really fathom what 10 to the 24 is, right? There's not that much money on the planet, right? That many dollars. Yeah, it's a big number, right? So then we divide by the radius of the Earth, right? So we'll say that chicken is not that far. Maybe we can add a meter to this, but that meter isn't going to register when we say that the radius of the Earth is 6.37 times 10 to the 6. Right, if I add 1 to that, it's going to be 6.370001. Is it just 2 zeros? No, three zeros. So that's not going to make a big difference, which is why that constant 9.81 is kind of the same whether I go to the top of Everest or I go, I'm at the water's edge in Vancouver. So let's see what that number gives us. I'm just going to pound on my calculator a bit here. And oh my goodness, it turns into 9.81. And so we can see that these two formulas actually work as long as we have the correct value for g. That g value depends on the planet. So if I'm on Mars or I'm on Neptune or Jupiter, that g value is dependent on the radius of the planet and the mass of the planet, okay? And of course, we know that the moon orbits the sun, orbits the Earth, which orbits the sun. We can also calculate the force of gravity if we know that the distance of the center of the moon to the Earth. We can see what the g value would be for the moon and calculate that force. Now, we had a problem in our last assignment about the satellite going around the Earth. So I'd like to revisit that using Fg. Now this satellite is far enough from the Earth that we cannot use 9.81. we have to use a different value. So here we have, I gave you the mass of the satellite to be, and there, let's write some givens down here. M1, or M of the Earth, will be 5.98 times 10 to the 24 kilograms. The mass of the satellite I gave you, thanks to students who are paying attention, 7980 kilograms. And the radius of the Earth, which we need because, remember, the radius of the Earth plus the distance to the satellite, right? We have this satellite here. So the distances here are do make a difference. So the distance from the Earth was given as 3.6 times 10 to the 7 meters, and the radius of the Earth is given as 6.37 times 10 to the 6 meters. So R, for our purposes, is 6.37 times 10 to the 6 plus 3.6 times 10 to the 7 meters, which, I don't know, can I do this in my head? That looks like 7, nope. Let's see, 360 plus 0.637. Nope, 360 plus 63.7. There we go. 4.237 times 10 to the 7 meters. Okay, well, and we also have G, right? G is equal to 6.67 times 10 to the 11. So let's plug that in. We have G, M of the Earth, M of the satellite, right, over R squared. 6.67, you can fast forward this if you want. 5.98 times 10 to the 24, and 7980, not a terribly big number. And we have 4.237 squared. Oh, times 10 to the 7 squared. And when we plug all that in, we get 1773 newtons. I believe when we calculated it in our assignment, we got 1788, something like that, newtons, which is pretty close, right? And we used centripetal force, right? We use Fc, m times, 4 pi squared r over t squared. I think we used that formula. And so you can see that the radius played a role there, but also even the time for one day, right, 24 hours, makes a difference there for the force. And so, yeah, pretty close to 2 significant digits. I'm happy with that. The last thing I want to emphasize is the difference between gravitational field strength, right? Gravitational field strength and force. These are not the same, right? Force is mass times the gravitational field strength. Ugh. All right, and the field strength, the gravitational field strength, is that number G that we talk about, right? So M times G, this is just the G. And the G is calculated based on the first mass, and usually the larger mass. We usually call it a planet or a star or something like that, okay? Yeah, lots of things. I really want to encourage you to do the caution activity at the end of lesson 22. So lesson 22, if you have a paper cup or something like that, I think it's a fun experiment you can try if you have a sibling or a parent who's willing to help you out. Just something to observe. You don't necessarily need to use colored water, but make sure you do it outside so you don't make a big mess in your kitchen. All right, well, do some problems. The project will be based on lessons 21, 22, and 23. We'll do lesson 23 and the elliptical orbits of planets next week.